Hi everyone, welcome to ICASSP 2022. Today we are going to talk about our paper Photon-Limited Deblurring using algorithm unrolling. This paper is presented by me, Yash Sanghvi, Abhinam Ganasambandam, and Professor Stanley H. Chan. All of us are at the Department of Electrical and Computer Engineering, Purdue University. Here is a preview of things to come. On the left, you can see a blurred and noisy image. The blur you can see are on the letters and the pandas arm, and the blur responsible is also provided in the kernel. The image is very grainy because of photon shot noise. On the right hand, you see our reconstruction using the proposed method. As you can see, the blur and the noise both have been removed. So our paper title is Photon-Limited Deblurring using algorithm unrolling. So let's talk about what photon-limited means here. So let's look at all these scenes taken in different illuminations. And on the left, you see there's a lot of noise, but on the right, you don't. So what you need to know about the image acquisition process here is that the number of photons hitting the sensor is a Poisson process. So on the left, the number of photons hitting the image sensor is very low. Since it's a Poisson process, the relative variance is large, and as a result of which the images on the left, taken in very low light settings, have a lot of photon shot noise. On the right hand, the number of photons hitting the sensor is very large, as a result of which the relative variance is very low. And hence, the noise, though present in the image, for all practical purpose, is insignificant. So whenever we refer to photon-limited scenes in this paper, we refer to scenes on the left where the shot noise is really dominant in the image. It can happen due to the fact that the scene is not well lit or the exposure time is very low. It can be either or both of them. So let's talk about photon-limited non-blind deblurring. The problem is recovering the clean image, the gradient clean image from the underlying noisy and blurred image using the blur kernel. Here is a mathematical formulation for the problem. Y represents the blurred and noisy image. It is modeled as follows. We take the clean image, we blur it by a motion kernel, or it can be also a Gaussian kernel, and we assume the blur kernel to be known. It is followed by degradation by Poisson noise. This photon level alpha represents a scalar, which you can think of as an SNR in this case. Alpha represents the average number of photons hitting the sensor. So higher the photon level, higher the SNR, and vice versa. Since there are a bunch of deconvolution approaches existing in the literature, we take one of them and try it on this problem. Here is the pre-trained network from the paper titled Deep Wiener Deconvolution, Wiener meets Deep Learning. It was published in NeurIPS 2020. And as you can see, it fails to clean up the image. But even though on noiseless cases, it works perfectly fine. Since existing approaches in the literature are designed for noiseless cases, we present our own solution for the Poisson deblurring case. Our approach involves using the plug-and-play priors. As you can see, the cost function in the equation represents the map estimate of the Poisson deblurring problem. Capital H represents the convolution operation in matrix form, and log of PZ represents the kernel, the image prior. The first step of plug-and-play requires us to take this convex optimization problem and convert into a constraint optimization problem using an extra variable z and the constraint x equal to z. We form the augmented Lagrangian and derive the plug-and-play updates. Here are the plug-and-play updates as you would obtain them from the Poisson deblurring problem. The first step, the x update, is the proximal operator for the negative log likelihood. In this case, it can be implemented as an optimization solver like memory-limited BFGS or any other gradient descent-based approach of your choice. Usually, in a Gaussian setting, this step would be a closed form expression. The second step, the proximal operator for the log prior, can be implemented as a denoiser and is a major insight of the plug-and-play approach. It can be replaced by a denoiser like UNIT, BM3D, or DNCNN. These three iterative updates collectively converge to the map estimate of the problem. Now that we have a bunch of iterative updates, we would like to perform algorithm unrolling to get a neural network out of it. What does that mean here? So we'll repeat the plug and play updates for, let's say, k equal to 8 iterations, and we fix the number of iterations. We can replace the z update by a denoiser, let's say a unit denoiser, and hence we can interpret this set of fixed iterations as a neural network and train it using a supervised loss. This approach has been used multiple times in image restoration and gives us the benefit of a neural network while having interpretability, where each single layer can be treated as an iteration of another approach. So we have an iterative approach and we're ready to perform algorithm unrolling using it. But wait, there is a minor roadblock. The X update, as you will remember from the previous slide, is a convex optimization solver. So when you're performing training, you need to backpropagate through this X update, which is not really feasible since X update itself is an iterative approach and you can't differentiate through it. And hence backpropagation doesn't work and this network is not really trainable. Since we are at a dead end, our solution requires reframing of the plug and play for this approach. Here's what we do here. You will remember this cost function from the couple of slides ago, and you will remember this constraint x equal to z. We add another variable v, which is a proxy for the noiseless variable. This approach has been proposed in a 20-year-old paper, Restoration of Poissonian Images using ADMM. So why do we use this approach? When we derive the augmented Lagrangian and derive the corresponding plug-and-play updates, here is what we get. Instead of 3, we have 5 updates here, and the first 3 updates are decomposable. The first update employs the Blur kernel and can be implemented by just FFTs. It can be viewed as a deblurring subiteration. The second update, the Z update, can be thought of as a denoising operator, nothing much different from the original plug and play. The V update is a Poisson proximal operator. This Poisson proximal operator doesn't use a Blur kernel, so it has a closed form. What's important is that all these iterations are differentiable, and you can use backpropagation through each of them, assuming the denoiser is also differentiable. So now that we have derived a set of iterative updates, we can unroll it using algorithm unrolling. Here is all the network architecture which we aim to train. X update, as seen before, is a deblurring operation and implemented by FFTs. The V update represents the Poisson proximal operator, and the Z update, which is a denoiser, is replaced by a unit structure. As a result of which, the network which you're going to train will have trainable parameters mostly consisting of the Z update denoiser. You can see there's another small network in the lower left corner, which is the hyperparameter network. Using the photon level alpha and the Blur kernel, it will predict the hyperparameters ρ1 and ρ2, which you need for X and V update. Now that we have a network ready to be trained, we train it using multi-scale L1 loss and using synthetic Poisson blurred images. Once we have trained the network, we compare it to other existing deconvolution approaches on the BSD100 dataset. We compare it with RGDN, recurrent gradient descent network, Purelette, deep Wiener deconvolution, and deep image prior. We compare it on different photon levels, alpha equal to 5, 10, 20, and 40, and isotropic Gaussian and motion kernels. You can pause the video now and see that we outperform all other deconvolution approaches by a large margin and across multiple photon levels. We also compare our approach on the Levin dataset, which consists entirely of motion blurred images. You can see we outperform other methods on PSNR and SSIM, except with alpha equal to 40, photon level alpha equal to 40, and where DPIR comes close enough to our approach. So BSD100 and Levin dataset Both contain either synthetic blur or synthetic noise. So, but there is no data set which contains realistic photon shot noise and blur. So, and we can verify our approach on it. So we created our own version of a deblurring data set for this problem. What we do is we go into a dark room, take a scene, reduce the illumination and point a camera and take images. What is important, we don't take the JPEG, but we also capture the raw sensor values coming out of the camera. Since we are talking about the non-blind deblurring problem, there is a point source. This point source is a 30 micrometer pinhole, which allows us to capture the blur kernel also responsible for the motion. At the end of the day, we have 30 blurred noisy images taken in low light, along with the blur kernel and the corresponding ground truth. We demonstrate that our method performs on these realistic photon shot noise images. What we do is we take each channel of this image, treat it as another grayscale image, and combine them using demosaicing to form an RGB image. Here are couple of reconstructions from the data set here. We zoom in and compare them to other existing deconvolution approaches. As you can see, qualitatively, we are doing better since the letters are much more legible in our approach. We also perform a quantitative evaluation where we are much ahead of the other deconvolution approaches. So to conclude, in this paper, we present an algorithm unrolling approach to Poisson deblurring. We specifically talk about how conventional plug and play is not really suited to this problem. And we show an alternate formulation, which is perfect for the algorithm unrolling approach. We compare our approach with other state-of-the-art deconvolution approaches on BSD100 and 11 dataset. We also provide a new dataset which has realistic motion blur and photon shot noise, and we outperform other approaches on that dataset as well. For folks who are interested in further details about the network architecture, the training, and the dataset, it is all available at our GitHub repository. And the link is given on the slide right now. Thank you for your time.